Let us look at the diagram here. In the y-axis, we are comparing the torsional moment acting onto the member against its torsional capacity. Whereas in the x-axis, it is a comparison between the shear force acting onto the member against its shear strength. When the ratio here is equals to 1.0, it means that the full capacity has been taken out by the torsional load. And when this ratio is equal to 1.0, that means the full shear strength has been taken out by the shear load. Now you see the parabolic curve here. It does not show in the manner of the square section here, which means that under the combined effect of the torsion and the shear load, the resistance over the torsion reduces as the shear load increases. If you view from the perspective of the shear load, the shear resistance does not maintain as the torsional load increases. In fact, the shear resistance reduces as the torsional load increases. This leads to a situation that this region is not achievable. In another word, because of these non-achievable regions, you might overestimate the resistance of the section if you do not consider the combined effect of the shear and torsion that happens concurrently in one section. To make it simple, if you are designing a section to resist torsional load alone without any shear load, you can freely use up 100% of the torsional resistance. Same goes to applications for the shear. If the member is only subjected to the shear load without any torsional load, you may also use up 100% of its shear capacity. However, if there are combined actions between the torsion and the shear, the torsional resistance capacity reduces and the shear resistance capacity also reduces. The degree of reduction would behave like a parabolic curve. Having this fundamental principle established, this will lead to revisions in terms of the design process for the member subjected to torsional load. The fundamental principle is still applied, just that we're going to use an interactive formula to cater for the combined effects of the shear and torsion. In fact, there are two interactive formulas here. One is meant for the sections with shear reinforcement. Another one is meant for the sections without shear reinforcement. We're going to discuss on that later. Let us first explain the concept of this interactive formula. Now imagine you have no shear load here. You can use up fully the torsional capacity. This whole thing here cannot be more than 1.0, as represented by this point here. Now, in the case that you have no torsional load, you can use up the full capacity in terms of the shear resistance. And this cannot be more than 1.0, as represented by this point here. Now, when you have both appears concurrently, the summations of this cannot be more than 1.0. These are representing any point in between. Let's say now you use up 10% of the torsional capacity, then you have 90% rooms for the shear. Let's say now you have used up 70% of the torsional moment capacity. This will left to you 30% of the room for the shear resistance. The summation here cannot be more than 1.0. By adjusting the quantum here and the summations not more than 1.0, this gives you a conservative measures to control the situations that you under design this section when they are combined effect, the shear and torsion. Now let us look into the formulas. TED represents the torsional moment acting onto the member. This is obtained through the analysis of the structure. TRD max represents the torsional resistance, the maximum resistance of the member. This one we have derived in our previous videos. The fundamental derivations give you this formula. Eurocode add in an additional strength reduction factor as a conservative measures. So what you see here, you have double layer of the conservative measure. First is the interactive equation here as a conservative measure under the combined effect of the torsion and the shear. Second, it will be the strength reduction factor as imposed by Eurocode. Purposely reduce a bit the maximum resistance to the torsion as a means of factor of safety in estimating the torsional resistance capacity. Next, it will be the shear part. VED is the shear loads that you analyze from the structure. VRD max represents the maximum shear resistance of the member. The formula for VRD max you may refer to the chapters regarding the shear load design as given in this slide. What you see here, as always, Eurocode apply a strength reduction factor in the calculations also, which eventually being reflected here. Now you see the strength reduction factors is also applicable to the maximum shear resistance. Get the dimensions of the member, concrete strength, find the shear angle. You will use the same angle here as per the shear angle. Substitute the relevant values and then make sure it does not exceed 1.0. Now in the case that it exceeds 1.0, you have various options to rectify this. Failure to fulfill this requirement means that the section will fail under the combined effect of torsion and shear. In order to rectify this, you may look into the formulas and see what are the components or parameters that you can modify in order to increase either the torsional resistance or the shear resistance. Very often, if you change the geometrical properties of the section, the geometrical property of the other part will also be changed. Therefore, while doing the calculations, if you have revised the sections, make sure you recalculate all the geometrical properties. The shear design here is meant for the entire section, whereas the torsional design here, it would be referring to an equivalent box section. Alternatively, you may modify the concrete strength. Higher concrete strength will give you greater resistance to the torsion and the shear. And then you will do the trial and error until this interactive formula pass. This is about the equations for the sections with shear reinforcement. What kind of sections that we are referring to? Normally, we refer to the beam sections or column section, where those sections you have shearing. Now you have another set of formula here. Compare with the sections that we discussed previously. The structure looks the same. The differences, it will be the capacity. Here we are referring to the maximum torsional capacity, which is derived on the basis of the imaginary truss model. Same goes to the shear resistance. However, in the sections without any shear reinforcement, you don't get the imaginary truss model. There is no compressive strut, Therefore, there won't be any formulas for you to find the strut angle. But the concept is still the same. You're comparing the torsional load against its capacity plus the shear load against its shear capacity. These summations cannot be more than 1.0. The torsional load and the shear loads can be calculated through structural analysis. Now the issue it will be the resistance of the member without any shear reinforcement. First, you might want to ask what kind of element that you are referring to. Normally, we refer to slabs, staircase, walls, where the cross-sections are relatively large, and the large cross-sections alone is sufficient to provide resistance to the shear load, and therefore, shear reinforcement is not required. Now, if you could recall our previous chapters regarding the design for the shear, when you encounter large sections like slab, which are lightly loaded, there is a process for you to calculate the shear capacity. You have shear resistance of the concrete with combinations of its longitudinal bar, and you have also the shear resistance of the concrete alone. This will be the shear resistance of the member without any shear reinforcement. We are using the same set of equations. Now, how about the torsional resistance of the member? You may make quick comparison in terms of the formula here. The structures of the formulas is similar, except that it does not constitute the shear angle. That means you have no compressive strut in this case, as it is not calculated on the strut model. And then your concrete property now is not governed by the compressive strength. Instead, it is governed by FCTK. FCTK stands for concrete stress tensile characteristics strength. That means we are talking about the tensile resistance of the concrete. Why is it so? This goes back to the fundamentals of the torsional response of the member. When a member is subjected to a twist, tensile stress develops within the member. This leads to spiral torsional crack along the member. Therefore, in the case that the sections is without any shear reinforcement, there is no concern with the compressive strength. Instead, it is more concerned with the tensile strength of the concrete. That's why you use FCTK instead of FCK. Having these two interactive equations introduced, let me do a quick summary. You know that under practical situations, torsions very seldom happen alone. It is very likely that shear and torsions happens together in a section. Now you cannot design for shear and torsion separately, assuming that it will perform as per the separate design when it comes to the combined situation. The resistance degraded under the combined shear and torsions effect. Review this curve here. The torsional resistance it will be at its max without shear load, but it will degrade with the increase of the shear load. Same goes to the shear. Without torsions, the resistance it will be its greatest. With the increase of the torsional load, the shear resistance decreases. That's why you will need the interactive formulas as a measures to cater for the combined effect of the torsion and the shear. The summations of the torsion and the shear cannot be more than 1.0. And then these interactive formulas come in two versions. One is meant for the sections with the shear reinforcement, for example, beams and columns. Another one is meant for the sections without shear reinforcement. This kind of sections has relatively larger cross-sectional area as compared to the load acting onto it. When the large cross-sectional areas has sufficient shear resistance, no reinforcement shall be required. For example, we are referring to the slab, staircase, or load-bearing walls. Although the structures of the interactive formulas look similar, they are actually developed on basis of different models. The one with shear reinforcements are developed from an imaginary truss model, whereas the one that without shear reinforcement, it will be purely reliance of the resistance of the concrete itself. I believe by now you have no issue with the resistance in terms of the shear without shear reinforcement and also with shear reinforcement. Just that the equations for torsional resistance you have to pay attention. First, for you to work out the TRD max, you need a strut angle, and this angle is obtained from the shear angle. Second, if you are talking about those without shear reinforcement, it has no concern with SCK. Instead, it is more relevant to FCTK. And since it is not developed on the imaginary truss model, no strut angle shall be required in the formula.